Welcome everyone, I'm Norman Wildberger. In today's video we are going to strengthen addition skills for young people. A very important activity that's really sort of a fundamental basis for success in mathematics. Okay, so what we're doing is we're going to lay out a way of thinking, kind of a program of proceeding in small stages, starting from very simple fundamental concepts and techniques to higher ones. So there will be a kind of an evolution of techniques that will develop. There will be some novel ideas and maybe even some notions that you have not run across before. But I think they will be important in strengthening our students' arithmetical skills. What we're aiming for ultimately is something like this, that when a student sees 1 plus 3 plus 5 plus 7 plus 9, here's what they do. They do it in their heads, okay? They say, okay, 1 plus 3 is 4. Add 5, that's 9. Add 7, that's 16. Add 9, that's 25. Another kind of example that we'll be looking more extensively in a later video is this kind of thing where you have essentially an arithmetical sequence built up by adding the same quantity. That's actually quite important. So here, to add up this 3 with all these 4's. 3 plus 4 is 7, plus 4 is 11, plus 4 is 15, plus 4 is 19, plus 4 is 23, plus 4 is 27. Okay. So that kind of facility to be able to do that smoothly, accurately, confidently is so important. And we're aiming then towards establishing the techniques that allow young people to develop those crucially important skills. Now, I want to emphasize very, very strongly, okay, that calculators are not part of this picture at all. Not at all. So as far as I'm concerned, K-6 students should not even know what a calculator is. They should not have ever seen one, okay? If there's one around, put it away, lock it up behind lock and key. Do not let the students rely on calculators. I know there are trends in modern education circles to use technology effectively and to introduce young children to calculators and computers at an early age. I think there's a role for computers, but not calculators. Okay? The actual arithmetical computations have to be done by the student. In fact, we are going to start by getting them to do these things mentally. Later on, when the numbers get bigger, they'll have to augment their mental skills with actual writing. Okay, that'll also be important. But at this stage, we're talking about adding relatively simple numbers, typically natural numbers less than 10 to themselves, perhaps a number of times. And for that, we can do it in our heads. The young children should be able to learn how to do that. That's what we're aiming for. Okay, so please, emphasis, no calculators at all in this story. Now, we've already seen the addition table. We're going to have another look at it today, but in sort of two halves. There's a kind of easy half to the addition table, and there's a harder half. And it makes sense to start with the easy half. Here's the easy half of the addition table. Numbers 1 to 10, numbers 1 to 10. The entries here represent the sum of the numbers in the left-hand column and in the top row. So 3 plus 4 is 7. 4 plus 5 is 9. 6 plus 3, circled here, is 9. And these are the results where the end result is a number less than or equal to 10. Okay, less than or equal to 10. So we've ignored all the other ones. Now, what we want to do is we want to get students just familiar with this half of the addition table so that it becomes rock solid, so that they immediately know that 4 plus 5 is 9, that 2 plus 7 is 9, that 3 plus 5 is 8, etc. And I remind you that when we're doing very simple addition like this, we can visualize what's going on in terms of our fundamental interpretation of natural numbers as row rectangles. Okay? That was what I suggested was a natural, very geometrical, physical representation of what a natural number actually is. So when we add 6 plus 3, what we're doing is we're taking this row rectangle with 1, 2, 3, 4, 5, 6 boxes, and this one with 3 boxes and adding them together. And that's a physical process resulting in a rectangle with 9 boxes. So this is the geometrical interpretation of this arithmetical thing that we want to keep in mind. All right? So behind each one of these additions, there's a little diagram like this that tells you what happens if you have a certain number of boxes and another certain number of boxes, and you put those two boxes together. Now let's introduce a useful terminology, the idea of complementary numbers. Now this has to do with the numbers on the table that add up to 10. Previous slide I put those in red. That's a particularly kind of important situation when you have two numbers adding up to 10, and so we give that a name. We say that they're complementary numbers. Two natural numbers are complementary if they sum to 10. So for example, 1 and 9 are complementary because 1 plus 9 is 10. 2 and 8 are complementary. 3 and 7 are complementary. 4 and 6 are complementary. And 5 and 5 are complementary. So 5 is complementary to itself. But we can also do it in the other way. So we can say 6 and 4 are complementary, or 7 and 3 are complementary, or 8 and 2 are complementary, or 9 and 1 are complementary. So the young child should learn all of these. So that 8 and 2, those are complementary numbers. There's something that twigs when they see 8 and 2 together. Those two numbers have a particularly important relationship. Now, we should say that this is because of the all-importance of our decimal number system, right? The fact that we're using the Hindu-Arabic system, which relies on powers of 10. That's why this notion is so important for our arithmetic. So we have very simple but fundamental questions like, what is the complement of 7? The child should immediately know that it's 3. Okay? No thought required. Complement of 5, it's 5. Complement of 4, it's 6, etc. Okay? So drill that into them, and geometrically that means that we're taking the two boxes that represent the two numbers, putting them together, and we get total sum of 10. That's sort of like a standard unit, an important unit for numbers. So a lot of effort must be put in to memorizing and understanding geometrically this easy half of the addition table. So when we have two natural numbers less than 10, whose sum is also less than or equal to 10. Okay? So now we can give students lots and lots of questions to practice. Okay? So they become familiar with these things, and so they're able to do these kinds of simple additions automatically without any thought at all. They just, boom, the answer is right there. 2 plus 5 is 7. 4 plus 3 is 7. 9 plus 1 is 10. 7 plus 1 is 8. 6 plus 3 is 9. 5 plus 5 is 10. 2 plus something is 5. That's a little bit trickier. Okay? So we still have to understand the story, but from a slightly different point of view. 2 plus 3 is 5. Okay, 2 plus 3 is 5. Something plus 1 is 7. 6 plus 1 is 7. 4 plus 4 is 8. 6 plus 1 is 7. 1 plus 4 is 5. 3 plus 5 is 8. Now, hopefully you can all do these things in your sleep, but it's important to get your child to be able to do these things in their sleep as well. And for this, a program of practice and training has to be put into place. It's not something that they just learn immediately from one day to another. And here's where educators have to step up and sort of enunciate programs of training. How do we train young children? What are the natural steps so that they become familiar with this half of the addition table? Okay. But in any case, they should be doing many, many problems just like this. And in fact, this is actually quite a good format, I think, where you have two numbers like this, and there's a blank somewhere, and they actually have to fill in the blank. Okay, so they have to write something, and they don't have to do much else. Okay, we're not asking them to rewrite the entire equation. We just want the answer, and we want them to write it down. It has to be legible and correct. And literally, you can give them hundreds of problems like this, and probably they should be given hundreds of problems. maybe even thousands. Okay, it doesn't take long. Once they're good at this, they can do a lot very quickly. And so we have to do so many that they're really good at this. And then we have to reinforce this. So as the years go by, maybe this is the very early years, as the years go by, we need to come back and revisit this kind of fundamental skill. Okay, so it's not just a skill for year 1 students. It's also a skill for higher year students. But of course, you can give them a little bit more sophisticated problems. And I'll show you a few of those later on. Okay. But so I want to emphasize that even though this video that I'm showing you now is a relatively short video, still the amount of training and practice required to absorb this material is very substantial. We're talking weeks, perhaps months of training for young people to ingest everything that's happening here and to become really fluid with the computations. So after some time, the student gains some confidence and competence, so we can go a little bit further. We can give them problems that involve several additions all at once. But these are still relatively easy in that the total sums that we get are still less than or equal to 10, so we're still always relying on that easier half of the addition table. And I suggest that these problems are done from left to right. So the student just automatically goes from left to right. So let me illustrate what they should be doing. So we need to add up 2 plus 1 plus 4. We start from the left. 2 plus 1 is 3. We just record that mentally, 3. And now we have to add 4. So it's 3 plus 4, which is 7. 1 plus 2 plus 5. 1 plus 2 is 3, plus 5 is 8. 3 plus 4 is 7. Plus 2 is 9, etc. We can have more than 3. 1 plus 1 is 2, plus 2 is 4, plus 1 is 5. 2 plus 1 is 3, plus 3 is 6, plus 1 is 7. So note the way I'm saying it. 2 plus 1 is 3, plus 1 is 4, plus 3 is 7, plus 1 is 8. Okay? So a kind of efficient mental way of going through it. So these problems should all be done mentally. We're just relying on our mental recall of the addition table, the easy half, and then subsequently performing more and more additions, always relying on that fundamental understanding that hopefully we have. So the only thing the student's actually writing down is the final answer, okay? None of the intermediate steps. Now we've talked about two numbers being complements of each other when they add up to 10. But there are other versions of that, kinds of complementarity, that are also useful for the students to know, associated not with the number 10, but with other lesser numbers. So for example, 9. 9 can be written as a sum of two natural numbers in a number of ways. And you can see that quite easily if you go back to the addition table and you just go down the diagonal that's going this way. There's a diagonal of 10s, and this just right above it, there's a diagonal of 9s. That illustrates all the pairs that sum to 9. So it's useful for students to see all of those pairs at the same time, to be able to compare them. Okay? So here I've given 1 plus 8 equals 2 plus 7 equals 3 plus 6 equals 4 plus 5 equals 5 plus 4, and you should actually complete this so you see all of them. Okay? So the student can look at all of these and get familiar with the idea that 2 plus 7 is the same as 3 plus 6, or it's the same as 5 plus 4. Maybe they can even think in terms of, well, to go from 2 plus 7 to 3 plus 6, we could do that without actually evaluating the sum as being 9, because the 2 has increased by 1, and the 7 has decreased by 1. So we got two numbers, we're adding them together, we're increasing the first, decreasing the second, so the sum is still the same. All right, that's sort of what's happening as we go from one of these to the next one. Here are the complementary pairs for 8. 8 is 1 plus 7, 2 plus 6, 3 plus 5, 4 plus 4, 5 plus 3, etc. And for 7, etc. Okay, so now we can ask different kinds of questions, such as 3 plus 5 equals 1 plus what? So this is a kind of a complementarity problem, but having to do with 8. So 3 plus 5 is 8. What else do we have to add to 1 to get 8? So we're really taking the 3 plus 5 here and the 1 plus 7, and those are being used here. Now, they don't have to memorize this exactly, but they just have to be familiar with it. We want them to see these pairs and become familiar with them. If they see them several times, they will start to get the hang of things. All right, that's what we want. So we have 2 plus something equals 3 plus 5, 6 plus something equals 1 plus 8, and so on. Okay, and I think this way of writing something where you write an equation and there's a line underneath representing a number that has to be determined is great, because the student can then just write the answer down on the question without having to repeat anything. After all, some of these students are very young. They may be in kindergarten or year 1. They're able to do this kind of problem, but they may not actually be very good at actual printing or writing. Okay? But hopefully they have learned how to express the natural numbers from 1 to 10. So after our children have learned the easier half of the addition table, now it's time to progress to the harder half, this part down here, where the numbers involved are bigger, and typically in the range from 10 to 20 instead of from 1 to 10. Okay, so they have to learn this. They have to learn that 4 plus 8 is 12, that 5 plus 9 is 14. Circled here, 7 plus 9 is 16. Okay, and you have to go through this line by line. You have to look at lots of examples. You have to illustrate things. Maybe use flashcards, whatever, it works. But one way or the other, you want them to learn all these additions. So this content has to be solidly memorized. There's various tricks for doing that. It's really not that much, because in fact there's a kind of a reflection symmetry, right? Once we know what 7 plus 9 is, then we also know what 9 plus 7 is, okay, because there's a symmetry here. So that's making the job simpler. And once we know that say 7 plus 9 is 16, well then 7 plus 8 is 1 less. There's sort of, you can connect the things that you do know with things that perhaps are not so solid. But one way or the other, students have to become really, really familiar with this addition table, especially this harder half of the addition table. It's crucial. Now, to make it easier for students to learn this, I think it's useful to have this geometrical underpinning of what's going on, which I call wrapping around 10. Okay. So what we're doing is we're kind of wrapping around 10. I want to illustrate what's going on here. So let's say we're interested in 8 plus 5. We want our student to understand what is 8 plus 5. Of course, eventually they'll learn that it's 13, and then they should memorize that. But we want them at least initially to see that that's really true. It's not just some arbitrary thing that we're memorizing. We're actually memorizing something that makes sense. Okay, so how do we see that? Well, here is 8 as a row rectangle, and here is 5 as a row rectangle. When we're adding them, what we're doing is we're putting those together to form a longer row rectangle. But with these bigger numbers, that's starting to get onerous, because it's hard to identify just how big such a longish row rectangle really is. So what we do is we employ a trick, or we lean on our base 10 system. The fact that tens are useful kind of units to separate out. So what we do is we take this 8, there's copied again in red, that's 8. And we remember that the complement of 8 is 2. Okay, so here's where the complementary understanding helps us. The complement of 8 is 2. In order to get 10 from 8, you have to add 2. So what we're going to do in our minds is we're going to take 2 of these 5 pieces, and we're going to join those with our 8 to make a row of 10. Okay, so 2 of those are going to go to the 8 to make a row of 10, and the other 3 are going to come down to form a new row. Now what we see is a row of 10 and a row of 3. That's a geometrical explanation of why 8 plus 5 is 13. It's because we've done this intermediate step of writing it first as 10 plus 3. So complementary numbers are a useful tool to make this happen. So in some sense, what we're actually doing is using the associative law, right? What we're doing is we're saying 8 plus 5 is the same as 8 plus 2 plus 3. We're breaking up the 5 in our minds as 2 and 3. And we're doing that because when we rearrange that as 8 plus 2 plus 3, these are complementary numbers. They add up to 10. Okay? They add up to 10, so we end up with 10 plus 3, which is 13. So this idea of going out to 10 units and then sort of carriage return, going to the new line, is a very useful one geometrically because it allows us to visualize larger numbers still using our row rectangle orientation. Okay, so let me show you that by introducing this thing which I might call a 10 table. So it's a piece of graph paper, okay, like a portion of the graph paper, a column, which is exactly 10 wide, 10 squares wide. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, okay? And how high it is, it doesn't matter. So we're going to use this to geometrically represent what happens when we add some numbers together, including this wraparound process associated with the harder half of the addition table. So let's say we have to add 2 plus 5 plus 8. Okay, so the 2, there it is right there. Okay, there's a 2. And maybe I'll just go like that to represent that 2. And then the next one's 5. I might do that in a different color to make it clearer. Okay, so now we have to add a rectangle of 5. Okay, starting there, 1, 2, 3, 4, 5. There's a rectangle of 5. We could actually outline it, but we're not going to keep doing that. Okay, there's a rectangle of 5. And now we have to add 8. And geometrically, what you can see we need to do is we need to think of this 8 as kind of breaking it up, okay? Breaking it up into 3 plus something else. Maybe I'll do it in a different color. So the 8 is going to be 3 plus 5. So here's where it's useful to know the complementary pairs that make up, say, something like 8. To know that 8 is 3 plus 5. Or maybe 2 plus 6 in another situation, or 1 plus 7, or 4 plus 4. Right? It's useful to know those complementary pairs even for other numbers, exactly for this reason. Okay, so what we've done is we've, maybe I should make this consistent, that's part of the rectangle of the 8, and here is the rest of it. We've kind of broken it up and put 1 on the line that we're on, and then the rest of it in the next line. And now the result is something that's easily readable because this is a row of 10. So we have a row of 10 with a row of 5. So we can say that this is 10 plus 5, which is 10, 5, or 15. Let's do another example like that. Say 6 plus 3 plus 4. Okay, I'll just do the 6. 1, 2, 3, 4, 5, 6. There's the 6. All right, and then the 3. I'll do it different. Okay, there's the 3. And now 4. 4 is, well, I need to break it up as 1 plus something else. So it will be 1 plus 3 more. What's the end result? The end result is that we have a 10 and a 3. 10 plus 3, that is 13. And let's do one more example. Let's say 5 plus 1 plus 7 plus 6. So 5 first, 1, 2, 3, 4, 5. There we go. And then 1. Okay, there's 1. And then 7. Okay, so 7, well, that's 4 of the 7. And then the complement of 4 with respect to 7 is 3. Okay, so we have to add 3. So we've cumulatively added 7, but we've wrapped around the 10. And we still have another 6 to go. Let's do it blue. So 1, 2, 3, 4, 5, 6. Okay, what do we see is the total? Well, there's a row of 10, and there's most of a row of 10, just 9 of them. So this is 10 plus 9 equals 19. Okay, so this is a geometrical technique where we're relying on a 10 table, which is part of a piece of graph paper, okay, which allows us to physically represent our numbers as row rectangles if we're willing to be flexible and wrap things around. So when we get to the end, we keep going on the next line, just like a typewriter, or I guess like a computer these days. Okay. So I think this is a nice technique that makes it clearer what's happening in terms of this wrapping around, and actually lends itself very easily to what happens when we go beyond numbers up to 20. Ultimately, we want to add numbers and get bigger and bigger numbers. Well, exactly the same principle allows us to actually add up and get totals bigger than 20. So we'll be talking about that in our next video. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.